Hi everyone, Constantin here. Today I'm going to tell you my journey, how I began with Elixir, and how we tried to implement a simple web crawler for one of our clients, as Chris said. And let's jump right into it. So 2 years back, we had this client who wanted an MVP for an app that was used for scanning products and delivering some interesting information about the products. So here's what we're going to talk about today. We're going to see what the data looks like a little bit, then how we're scraping the data, crawling with the stream, talk a little about concurrency and parallelism and how that was useful for us, and also a little bit about ethical web crawling. Now, we had the client, he wanted an MVP to scan some products, but there was a problem. We didn't have access to APIs. However, we got the green light to scrape the data from those websites. So this is how everything started for us. So let's see how we scrape the data. So basically what we had access to websites like this. This is a website for playing around with web crawling. So these are mocked data. And we had similar structure of the website. So what we had to do is to go inside each product and get the UPC from each product in part. Now, the way to do this, for those of you who have experience with the web development, is pretty simple. If you go to the HTML of each page, you can see the HTML structure. And what we had to do is actually get all the pages that contain products and search for the UPC of the product. Now, in order to implement that, we started with an interesting tool called Floki, and also coupled it with HTTP Poison, which is a client for making HTTP requests.
Constantin, sorry to interrupt you. I just wanted to make sure did you have a slide deck to share during this talk?
Oh, sorry. I thought I was sharing it. Sorry.
No worries. No worries. Just wanted to make sure.
All right. So let me get back to it. My mistake. Sorry about that. All right. So here we are. Okay. So this is the stuff that we're going to talk about: introduction, scraping, crawling, concurrency and parallelism, and then some ethical web crawling. All right. So we're here. I was showing you the website as an example for what we were scraping for, right? We have this website, Books to Scrape, which is specifically created for playing around with the web crawling. So what we want to do is go inside each book and find this element here. Now, if we look with inspect in the HTML, we can see the structure, and then we can apply some rules with a nice tool called Floki, which is, I think, the most used for scraping, parsing HTML data for Elixir. So what we have to do is simply go to the table, find the first row, and get this data here. All right, so what we did is, this is a stripped down version of our implementation. Basically, this is the function that does all the scraping. So the first step is to get the page by making an HTTP request, with HTTP Poison, and then apply Floki parse document to get the parse data. And this may seem familiar to some of you. this is like a CSS selector, and what we want to do is to look for all the anchors or URLs and get the URLs from there. Now, at this point, we're not looking for this. We're looking for a way to build the crawler. So we'll get to the point. All right, so here it is. Here's the way we're going to take all the data from the UPC from the page. All right, we'll go for a table, go for the first row, and then get the text from the cell. Right. Now, this is pretty much it about scraping. And now we want to see how to implement the crawler. Now, crawling is an interesting thing because at first, because this was the first project related to crawling, we had two options. Either go really loyal to the structure for each website, right? We can do it in two ways. We can find all the URLs on each website like this. If we see a structure, we can generate all these URLs, page 1, page 2, so on and so forth. And then for each one of them, scrape the URLs for each product, and then on a third page, find the UPC inside each of those pages. There's a problem with this. If we make our algorithm to follow the structure, it's very hard to go to scrape another website, right? Because we have to rewrite all the rules, and not everybody has this type of structure. So we had to have a generic way of scraping any website, right? We just provide the root URL and then provide a function that would get the data for each page. This way, we had to crawl, right? And if we were to go with the initial version, we would go with an eager version where we had to know all the URLs from the start before starting to do the scraping. But we can go with a lazy version. Now, eager versus lazy, this is an interesting topic. Eager would, you probably know about this because you definitely played a little bit with things like this, right? Sometimes you want to generate a number of items, right? Like, let's say we want numbers 1 to 5, 1, 2, 3, and 5, 4, and 5, right? And we have it. And there's a problem with this because we have to keep this list in memory, and we have to know about it before using it. Imagine we would have 1 million of these. It would be not very easy to do operations with it in terms of memory and processing and so on. But we have another option. We can use a range. Right? We can do it like this. And this is just a function. This is not an enumerable that has all the values ready to go to be processed, right? This is a function that will generate as we consume, as we enumerate the collection. So this is a function. Now, the way I started, the way I remember it easily is with a joke like this. If you're fans of Friends, the eager version will always provide means that the data is always there, where the lazy version is it will be generated. So a stream basically will generate the elements as we consume it. So what does that mean for us? So for us, it meant that, of course, we want this because we don't know how many links a website has, and we want a way to be able to generate future links based on existing links. So what do I mean by that? So if I have this link, for instance, I want to gather all these links and then emit them for the consumer. So this is something that works for us because we don't know when this is going to end, and we don't have to keep it in memory all the time. All right, so in order to achieve this, we can use stream resource. So stream resource is really interesting because we can create a stream, we can wrap a resource and create a stream out of it. So we can actually create the range by implementing our own version of it. So a stream would have a start function where we give it some initial data. Next function where we generate the next state and also the elements that will be emitted to the consumer, and also an end function that we might want to call once the stream finished. So this is what we used in the end for implementing the crawler. Now let's have a deeper dive into this implementation. So here's what we have. This is the way we scrape a URL, right? We provide a URL, and then we have a scraper function that would take the relevant data that we need. So we do this get for getting the page. We parse it, and then we find all URLs within the page. Now, there's an interesting issue when we do this. There's an extra step, and Elixir is really helpful with this. Now, sometimes the URLs that we get are not very helpful. Just a second. Because we have things like this, right? We have relative paths. What this means is that when we get the attribute href, we will get this thing. But this thing doesn't mean anything without some context, right? And the context is this root here, which is the root of the URL. If I put this here, it doesn't mean anything. So with Elixir, we can use a nice function that would merge the link that we found with the link that provided the HTML that we found the link from. And this would merge it and give us the absolute URL that we will use later on. All right, so this is the way that we scrape the data. And then this is a helper function, because we would always start with a list of URLs that we want to scrape. And this is the actual implementation of the stream. So what do we have here? We have the following. This is the initial state. We have a start URL. In our case, this is the root URL for books to scrape. So basically this one here. And the next function would be a little bit more complex, and we have several cases here. One case is when we don't receive anything from the next function, right? From a previous step. Like if we get to a point where we don't get any new URLs that we have to crawl, that means that we crawled everything that was possible to crawl on the website. So we tell the stream to stop. Otherwise, it would go on and on. Right. In the general case, we would have the URLs that we have to scrape, and also some cache for URLs that we already scraped. This is very important because we would run into the problem of loops, and our crawler would never stop. So an example for this is the fact that basically on any page, we will have this homepage URL, right? And this is because it's present everywhere on each page, we will always rerun it. Okay, after we do this, we have to do some cleansing of the data. Basically, our scrape function will retrieve a tuple of two things. One is the new URLs to scrape, and the other is the data to be emitted to the consumer. So what we want to do, we might want to flatten, because we receive a list of URLs. We will flatten it, remove the duplicates, and this is another important step. We want to make sure that we stay within the limits of our website that we're scraping. Otherwise, if our website contains a link to Google or Wikipedia or any other website, it will go wild and never stop unless we tell it to. Okay, then we want to make sure that we add the URLs that we already scraped to the cache of found URLs or previously scraped URLs. So this is pretty much it for scraping the URLs, for implementing the crawling, sorry. Now, let's move on to some other interesting topic. Concurrency versus parallelism. Once we got this thing running, it was interesting to see how fast it was running. And we had the feeling that it was a little bit slow, and we wanted to improve the performance. And our first thought, and even our client's thought, was, okay, let's buy some more power to do it. And we were a little bit hesitant because we wanted to see what the actual problem is. And we got to this discussion. And the difference between concurrency and parallelism is really interesting and quite important. Now, what's the subtle but important difference between the two? The answer is straight in the names, right? Concurrency and parallelism. Parallelism means that things actually happen in parallel, while concurrency, it's rather an illusion of parallelism, right? It's for instance, when you have a web page, a web server, you have the illusion that a lot of users are having their own session, right? But they use the same server probably. Okay, just a quick question. Can you hear me well? Because I see Chris asking me if my mic is working.
Don't worry about that. Sorry, that's me talking to our next speaker.
Oh, okay. Thanks. All right. So this is really important, because in the end, it tells us if we actually need more resources, or we can solve our problem with the existing resources. So let's do some tests. Let's see how our crawler behaves. So what we want to have here is the following. We would like to start scraping something. So I'm going to get this and run it here. All right. So this seems to be working quite well, but you may notice that it's not really fast, and it's going to take quite some time to scrape all the data. So I'm going to stop it now, and check some interesting things. All right, let's see how many cores we have available. We can do this by using this nice tool, observer, and we can have valuable information here about our environment, right? We have 12 CPUs available for use, but there's a problem. We have only one scheduler. So by default, when you start the VM for Elixir, there will be a pairing number of schedulers per CPUs, which means if you have 12, you will have 12 schedulers. I did a little trick here, and when I started the project, I added a little flag here, which specifies to use just one core. So that's what happened. So maybe you have noticed that I also printed the process ID, and it's the same for all of them. So the first thing for us was, okay, we have one core, and we're doing a map on each URL. So how can we make it a little bit faster by not make it sequential, but asynchronously? So in Elixir, this is quite easy. What we have to do is simply switch from this to this. So we can use task async stream, and we would instantly have concurrency, which is pretty neat. So let's recompile and check the right, here it is. It feels a lot faster. And you can also see the process ID. It's different for each URL. And once this is finished, we can also check the observer to investigate the number of cores, which will be the same as previously. I'm going to stop it now because it doesn't make sense to wait this long. So it's faster. We can see that it's still one scheduler available, but it's much faster than the previous version. Now, here's an interesting thought. Now I started with one core. What would happen if I would put 12 cores there? Right? So what we would achieve here is not just concurrency, but parallelism as well. So we will start this, and we can start our crawler. So it's still fast, but I would argue it's not faster than using just one core. And there's a good reason for that. We have to understand the problem that we're trying to use. And the reason for that is because we can get to an embarrassingly parallel solution, or we can simply use less resources to get the same result. The reason for, so we have 24 seconds, right, for running the crawler on all 12 cores. I'll just run it in the background for one core and see the difference. So 24 seconds, and I'm gonna run it. The reason is because our crawler is waiting on response, right? This is a problem, an input-output bound problem. It's not a CPU bound problem. If we have to wait a lot of time, we can just take the resource and give it to some other task to do his job as well. And this is the case because we make a request to a website, and then we have to wait for the response. While waiting, there's no need to keep it blocked. So we can just give it to another process. So here it is. There's 32 seconds. It's not divided by 12. It's pretty close. If we would have a problem where we need to do a lot of number crunching, we would use parallelism. Like if you have a video game, or I don't know, mining for crypto or things like that. There, concurrency is not very helpful. All right, so this is an interesting analysis, and for us it was helpful to understand that we do not need to purchase more processing power. Okay, now we get to one more minute or two for ethical web crawling. Web crawlers are really useful in many use cases, but they can also be very dangerous for the ones that have websites to be crawled. Now, before implementing a web crawler, it's very good to read the terms of use and also the robots.txt. A robots.txt would instruct your web crawler to limit the number of requests and also to apply some delays between requests. It's very easy to find it. If we go to Wikipedia, for instance, and /robots.txt, we get a huge list of rules for different types of bots that scrape it. Another thing would be to identify yourself when sending the requests. So there's a important header user agent that you have to set with information about yourself. Set timeouts. Don't take advantage, because many websites do not have the robots.txt. They are not even aware of this. And if that's the case, contact the site owners to inform them about the thing that you're about to do. This is the case for us. That's what we did, and we got the green light. Okay, so this was me, and thank you very much for listening, and I hope this was useful. Cheers.